All right, very good evening. So now we'll talk about conduction with thermal energy generation for the case of cylinders and spheres. In the last class, we derived the expression for heat conduction with thermal energy generation for plane walls. So now we are going to derive this expression for different geometry, mainly cylinder and spheres. So let us first review this problem. So actually the concept is very similar for heat conduction through a cylinder. Only thing actually we have to consider that there is a heat generation, right? So in order to derive the expression, what we have assumed, we have assumed a cylindrical rods with one-dimensional radial conduction. So the heat is conducting in the radial direction. Okay, nothing in the across the length. We are considering the radius of the rod is capital R, length of the rod, cylindrical rod is capital A, thermal conductivity is given by K. And also we considered QG, as you can see, is the uniform volumetric heat generation per unit volume per unit time. Right? H is the heat transfer coefficient to the atmosphere, that is the convective heat transfer coefficient, and ambient temperature we are considering it TA. Okay, so this is all the parameters actually given here. This is a cylindrical rod, you can see the blue lines. Ambient convective heat transfer coefficient given by H, ambient temperature given by TA, the wall temperature of the cylinder given by TW. The radius is capital R, but we are considering a small incremental radius of R with an incremental radius of dr. Right? So let's see what happens. In order to obtain the temperature distribution, we have to consider an element of radius R and thickness of dr. This is the element of R, thickness of dr. You can see here. This is the front. This is the front view. So heat conducted at radius R, small r can be given by Q minus 2 pi RL into K dt by dr. This is a well-known expression for the Fourier's law, right? Now heat generated in this element, just like the last class, if you assume that heat generated is capital QG, that will be given by QG 2 pi R dr into dl, right? That is the volume, right? 2 pi R dr dl is the volume, and QG is actually already mentioned unit of volumetric heat generation per unit volume per unit time. So what will be happening in that heat conduction? So we are considering that heat is being generated in this small strip, right? So heat is going to be generated. Heat is generated. Heat input is at this surface, and then heat output at this surface. So heat conduction at radius R plus dr. So this is R plus dr only at this surface, right? Will be given by QR plus dr, QR plus dt by d by R QR dr, right? So that is the incremental amount of heat which is being generated over a distance of dr, right? Over a thickness of dr, right? That is the total amount of heat being conducted out. Now using the steady state condition, we have already know QR, right? So we can substitute the value of QR. So QR plus dr will be QR plus this. This is actually QR plus QG. QR plus QG is equal to QR plus R, right? That is the total amount of heat being generated, because this is the whole input plus being heat generated will be the total amount of heat being dissipated. Now QR plus dr already determined QR d by dr QR dr. So QR get cancelled. We finally get QG d by dr QR dr. Now QG already have derived QG 2 pi R dr dr. We substitute that value. D by dr again QR also we have derived. We substitute this value. Then rearranging the term, we get d by dr r dt by dr equal to minus QG by K into R. I hope you understand up to this point, right? Only we are changing. We are just rearranging the term, right? Now, if you do the double integration with proper boundary condition, first integration will give you R dt by R equal to minus QG by K R square by 2 C1, right? And then if you again do the derivation, sorry, just again rearrange the term, divide by R, we get dt by dr minus QG by K R by 2 plus C1 by R. Then if you again do the integration of this, you get T equal to QG by K minus QG by K R square by 4 plus C1 log R plus C2, right? I hope so. This expression you have if you have done perform double integration, you get past this term, then you divide by R, you get this term, and then again if you do the integration, you get finally this term. So you have to know the constant, this constant of integration C1 and C2. How to evaluate? We have to evaluate using the proper boundary condition. Now at R equal to R, that is at the surface. R equal to R means the surface cylindrical rod surface is capital R. temperature will be wall temperature, that is TW, already have seen, right? TW. So that is number one boundary condition. And then second is heat generated will be equal to heat loss by conduction at the rod surface, because we are just considering this heat being generated is going to be dissipated. So if from the second boundary condition, heat generated is this term, right? QR 2 pi r dr. So QG 2 pi r dr at the surface, small r will be substituted by capital R. So QG 2 pi r square L, right? Pi r square L, that is the amount of heat being generated, and then is equal to, that is going to be equal to the this amount of heat, right? Minus K 2 pi r L dt by dr. Minus K 2 pi r L dt by dr when r is equal to r. So this simple, this term we have integrated here, right? Because if we do the integration of this, we get this term. If we do Qg 2 pi r dr dl, I think okay. So this is the terminology. So then at r equal to 0, dt by dr is 0, right? So if you put r equal to 0, dt by dr 0, since in the case of cylinder, center line is the line of symmetry, so the temperature gradient dt by dr at the surface, that is at r equal to r given by, so you just substitute dt by dr when r equal to r, and then you receive this particular expression. If you rearrange, we get dt by dr minus Qg by K r by 2 plus C1 by r. We are getting from the 2.106. This is actually coming from 2.106. And from this expression, we can say that when r is equal to r, you get just divided by this minus Qg by K r by 2, right? From this expression. So we can see dt by dr r equal to r from the 2.106 is this, and from this heat from the boundary condition 2 is actually this. So you can equal these two, and if you equal these two, you get C1 equal to 0, right? Now again, applying the boundary condition equal to r is equal to r, t equal to tw at equation 2.107, this expression. If you put this value, then you get this expression, then C2 will be this term. So you already get C1 and C2, and then if you put this value into this equation 2.107, then we get finally T equal to minus Tt by K r square by 4 plus Tw plus Qg by K r square by 4. And then you rearrange this, and then you get T equal to Tw Qg by plus Qg by 4K into r square minus r square. So this is the expression, and this is a parabolic expression, right? And how to get the maximum temperature? The maximum temperature will happen when small r is equal to 0. If small r is equal to 0, T will become T max, and this will become T max become Tw plus Qg by 4K r square. So if you divide 2.108 divided by 2.109, then you get T minus Tw, T max minus Tw. And this right hand side divided by this side. So actually all this term get cancelled, you get minus 1 minus r by r whole square. So finally, this is the expression T minus Tw is equal to T max minus Tw equal to 1 minus r by r whole square. This is a parabolic expression. How to get the energy generated within the rod per unit volume? That will be equal to energy dissipated per unit height by conduction. Right? So energy generated already have seen Qg by pi r square into L, right? That is the volume. Pi r square is the volume, and there is the Qg is the amount of heat generated per unit volume per unit time. And then it will be equal to energy dissipated by convection. That will be 2 pi r LH Tw minus Ta, right? Because we are considering that the ambient temperature is Ta and wall temperature was Tw. So that's why that much heat is going to be dissipated by convection, and convective heat transfer coefficient given by H, and the area is given by 2 pi r. So then in this expression, if you equal, then you get Tw equal to Ta plus Qg by 2H into R. Very good. So if you get this value Tw, you can substitute this expression 2.111 into 2.108. That is this expression, right? So you get T equal to Tw is now this Ta plus Qg by 2H into R plus Qg by 4K r square minus R. And the value of Tmax happen when R is equal to 0. So Tmax will be Ta plus Qg by 2H into R, Qg by 4K r square, because R becomes 0. That's all. It's very simple, only a little bit cumbersome. There are a lot of equations and expressions, but if you follow it thoroughly, you can derive all the expressions. It's not very difficult. Okay. So let us look into the numericals, couple of numericals, so it becomes easy for you. Current of 300 amperes passes through a stainless steel wire of 2.5 millimeter diameter and thermal conductivity given 20 watt per meters per C. The resistivity of the wire is 70 into 10 to the power minus 8 ohm meter and the length of the wire is 2 meter. If the wire is submerged in a fluid maintained at 50 C and convective transfer coefficient at the wire surface is given 4000 watt per meters per C, calculate the steady state temperature at the center and at the surface of the wire. So this is the problem. This is the wire, stainless steel wire. It's 2.5 meter diameter, and then it is temperature is given TW, ambient temperature is given 50 C, right? The wire thermal conductivity is 20 watt per meter C, and the heat is being conducted, right? And the fluid heat, convective transfer coefficient given 4000 watt per meter per C. So R is radius, diameter is given 2.5 millimeter. So the radius will be 1.25 millimeter. Thermal conductivity given, resistivity given, L, all the ambient temperature given, I is also given. So temperature at the surface of the wire and at the center of the wire, right? Rate of heat generation, what is the rate of heat generation? This is a thermal wire, right? It's a Joule heating type of thing, right? If you know that Joule heating, that is I square R, right? So that is actually you're using. That amount of heat generation is actually current whole square of current times the resistance, I square R. That is called Joule heating. So I square R, now R is actually can be given by the rho L by A, right? It's the rho is the resistivity, electrical resistance. So rate of heat generation actually per unit volume Qg by AL, because AL is the volume of the wire, right? So that you can write in I square rho L by A divided by into 1 by L. So actually L and get cancelled, it become rho into I by A whole square, right? Now rho you have known, right? Rho it's given, right? The estimate is given 1700 minus 8. I known, A known, right? So if you put this value, then you get the Qg 26.14 10 to the power 8 watt per meter. The temperature at the surface of the wire, it should be straightforward. The formula TW equal to TA, Qg by 2HR. TA you know, all the parameters you know, you put it, and then you get 458.44. That's the formula. Temperature at the center, where at the center of the wire is given by the maximum temperature. That is, this is the maximum temperature, center of the tube, right? TW plus Qg by 4K into R square, right? So again, the same formula. I think already you have derived. So you put the value and then you get 509.6. You see, very simple. This part is very simple. Only thing, you have to derive this expression, the Qg, right? Using this concept. I hope you understood this. Look into the another problem. A 3 millimeter diameter stainless steel wire. Thermal conductivity K is given 20 watt per meter C. Resistivity given rho n into 10 to the power 4 ohm meters. 1000 meter long, has a voltage of 100 volt impressed on it. The outer surface of the wire is maintained at 100 C. Calculate the center temperature of the wire. If the heated wire is submerged in a fluid maintained at 50 C, find the heat transfer coefficient on the surface of the wire. Second, radius of the stainless steel given 1.5 millimeter, length of the wire given, voltage impulse given, thermal conductivity, resistivity, all the parameters given. Temperature of the outer surface of the wire is given 100 C, right? Fluid temperature given, ambient temperature 50 C. So electrical resistance rho L by A, you calculate this. Rate of heat generation V into I or I square into I. Same I square into R, you know already, right? Or V square by RE, right? Actually, just simple I square by I, you just substituting the value of instead of I, you are putting some voltage here, right? V square by R, you will get 7065 watt. Rate of heat generation simple. Again, the same formula what we have used in the previous numerical Qg by L. You get 9.998 10 to the power 6 watt per meter. But rest of the part is very easy. Center maximum temperature will be TW plus Pg by 4K R square. You get 100.28. Heat transfer coefficient you have to get same formula. You have to use this formula in the previous expression. Only thing here now you have calculated T max. You have calculated, you know TW, right? Ambient temperature, you know, all the parameters known except H. So you solve it for H and you get 149.97 watt per meter square. Let's look into another examples. The meat rolls of 25 millimeter diameter having thermal conductivity 1 watt per meter square are heated up with the help of a microwave heating for roasting. The center temperature of the roll is maintained at 100 C when the surrounding temperature is 30 C. The heat transfer coefficient on the surface of the meat roll is given 20 watt per meter square C. Find the microwave heating capacity required in watt per meter C. Very good. So, radius given, thermal conductivity given, maximum temperature given at the central line, right? Ambient temperature given. Thermal conductivity also given, right? So, we know that temperature formula, right? T max equal to TA plus QG by 2H into R plus QG by 4K into R square, right? So, you put the value of here except QG, right? Because you don't know the heating capacity. You solve for QG, you get 1.991 10 to the power 5 watt per meter. So, that is the heating capacity of the meat roll, like microwave. Another problem. A chemical reaction takes place in a packed bed. Thermal conductivity 0.6 meter per C. Thermal conductivity is given. Between two coaxial cylinders with radius 15 mm and 45 mm. There is a coaxial radius. Right? The inner surface is at 580 C. You can see, and it is insulated. Assuming the reaction rate 0.55 milliwatt per meter cube in the reactor volume, find the temperature at the outer surface of the reactor. You have to determine the outer surface temperature of the reactor. This is the insulation. Inside radius is given 15 mm, outside given 45 mm, as you can see. Okay. The packed bed thermal conductivity is given 0.6 watt per meter square. All the parameters are given, right? Only you have to determine the outer surface temperature here, right? This temperature. Temperature of the outer surface T2, I think here the figure is given, R1 given, R2 given, heat generation QG also given 0.55 milliwatt per meter cube. Inside temperature T1 given 580 C. Now temperature of the outer surface T2 can be from the given problem the constant differential equation. Remember the differential equation you use, right? P by dr R dt by R plus Qg by K dr. By integrating the above equation twice, we get T plus Qg by K R square by 4 C1 ln R plus C2. This is the same expression, right? Now in order to evaluate, now things will be a little different here. In order to evaluate C1 and C2 using the following boundary condition, we have when R is equal to R1, that is here. There is not, because of the insulation, no thermal temperature difference happens. So dt by dr 0. So you get C1 Qg plus by K R1 plus 2. At R is equal to R1 again, T equal to T1, right? So equal to put again the value T equal to T1. Already have determined C1. So you put all this value, then you get C2 is equal to this. Okay. Now substituting this value on the integration in the equation 2, you get T plus Qg by K R square by 4. C1 you determine Qg by K R square R1 equals to ln R, and C2 you have determined this, right? T1 minus Qg by K R1 square to ln R1 minus 4. You have to rearrange all this term, and then finally you get this expression. Now you have to determine T2. As T become T2, when R is equal to R2, you instead of T you equal T2 and R2, and all the parameters are known. You solve for it, and then you get 280.7. So actually, the thing is very simple. Only thing you have to boundary condition are different because it is a concentric cylinder. There are two cylinders. So this is actually the concept for concentric cylinder. This numerical. When there are two cylinders, then how to get the expression using the boundary condition. So up to this point, this cylinder. Let's look into the spheres with uniform heat generations. Similar concept we have to use, but I will explain it so that it becomes easy for it. Consider one-dimensional radial conduction of heat under steady-state condition through a sphere having an uniform heat generation. So we are considering the outside radius of the sphere, capital R. You can see K is the thermal conductivity of the sphere. This sphere. Qg is the uniform heat generation per unit volume. This is the small uniform heat generation by Qg. Tw is the temperature of the outside surface or wall of the sphere. Here, this is Tw. Ta is the ambient temperature here. So heat conducted at a radius R is given by Q minus Ka dt by dr, where area is the 4 pi R square. You already know, right? Heat generated will be Qga into dr. Now area will be 4 pi R square. Qg into 4 pi R square dr. Heat conducted out at radius r plus dr. We are considering small strip of dr thickness. So at this surface, what is the heat conducted? It is qr plus dr equal to qr dt by dr, d by dr, qr dr. Now under steady state condition, qr plus qg, that is the heat input at this surface, and heat generation will be equal to the heat conducted. So qr plus qg equal to qr plus dr. Qr plus dr equal to qr d by dr, qr dr. Qr get cancelled, you get qg equal to d by dr, qr dr. Same, just like the cylinder one. Now you put the value of qg here and divide, and qr you know, right? This is the expression. So qg becomes qg 4 pi r square into dr, and then this integration you can take 4 pi k constant out. It becomes d by dr r square dt by dr into r dr. So you divide it by r square. So if you divide it by r square, it becomes 1 by r square d by dr r square dt by dr plus qd by k equal to 0. Both sides you have determined, divided by 4 pi r square k and dr. Right. So actually this term has been rearranged. Now you can write this expression equal to 1 by r square d by dr r square dt dr. There are two variables, so you can take the partial differential equation, partial derivative. So 1 by r square, when r square constant will become d2t by dr2 plus dt dr constant will become d by 2r dr dt dr. I hope you understand. This is just a partial differential equation plus qg k equal to 0. So you take again r square out, so it becomes d2t by dr2 plus 2 by r dt by dr equal to qg by k equal to 0. Now again you multiply by it r, so it becomes dr d2t by dr2 into 2 by 2 dt by dr plus qg r by k equal to 0. Now r d2t by dr2 and then 2 dt by dr can be written dt by dr plus dt by dr plus qg by r equal to 0. Now these two terms again you can take into a partial differential form. You can take d by dr out, so it will become r dt by dr, right? Because if you take r constant, then it will become dt by dr, r dt by dr. Sorry, if you take r out, then it will become d2t by dr, right? And then if you take r, it will be here. This here no, there will be no. I think. Now again, if you do integration, then it become r dt by dr equal to multiply by r square. So if you multiply by r square, it will become r dt by dr, and it become t because we are multiplying by r dr. So the integration of dt will become t, and this will be r dt by dr plus qg by k r square by 2 equal to cr. Again, you take these two terms d by dr rt, because these two terms you can take into partial differential form plus qg by k r square by 2 plus cr. Again, if you integrate, this become rt qg by k r cube by 6 plus c1 r c2. That's c1 c2 constants. Actually, both this term actually double integration are doing. Now at the center of the sphere r equal to 0, c2 becomes 0. If r 0, c2 becomes 0. And at an appropriate boundary condition at r is equal to capital R, t equal to tw. We get r tw qg by k r cube by 6 c1. So c1 is this term, tw plus pg by 6k plus r. So you get the value of c1 and c2. You put it here. C2 is already 0. You get rt plus qg by k r cube by 6 plus tw qg by 6k r square by r. Then rearrange this term divided by r. So we finally get t equal to tw plus qg by 6k r square minus r square. Now maximum temperature will be at the center when a small r equal to 0. So this becomes 0, T max will become tw plus qg by 6k r square. So you divided this by this, you get T minus tw, T max minus tw, 1 minus r by r. See, most important, see this term and T minus tw, T max minus tw, 1 minus r by r whole square is same like for sphere as well as for cylinders. Now integrating the Fourier equation for heat flow, we have Q equal to minus k dt by dr, r is equal to r, minus k 4 pi r square dt by area is 4 pi r square dt by dr. Now t is, we have determined this, right? So substitute the value of t, tw plus qg by 6k r square and r square is r equal to r. So if you put small r equal to capital R, Then if you take the derivative of this is constant, it will become minus 2r, right? So minus k 4 pi r square minus 2r by qg by 6k, right? That is what is happening. And then if you put the value of r is equal to capital R, this term become like this. So amount of heat generated is equal to 4 by 3 pi r cube qg, that is volume of sphere into heat generation capacity. This heat conducted is equal to heat generated. Right? This is the amount of heat generated. And heat conducted is h 4 pi r square Tw minus Ta. This is the term, right? Because area is 4 pi r square, conductive heat transportation H, and the amount of heat dissipated to the atmosphere is wall temperature minus atmospheric temperature. So if you rearrange this, then Tw is equal to Ta Qg by R by Th. Now, if you put this value of Tw into 2.1.2, this is the expression, right? Original expression. Then it becomes T equal to Ta plus Qg by R Th plus Qg by 6k R square and R square. The maximum temperature is when small r equal to 0, it becomes Ta plus Qg by Th R plus Qg by 6k R square. This becomes 0. I hope you understand this thing. This expression will be easier. Let us look into a numerical. An approximately spherical shaped orange thermal conductivity given 0.23 watt per meter C. 90 mm in diameter undergoes ripening process and generates 5100 watt per meter cube energy. The external surface of the orange is at 8 C. Determine temperature at the center of the orange and heat flow from the outer surface of the orange. Outside the radius of the orange given 45 mm. Rate of heat generation given 5100 watt per meter cube. Wall temperature given 8 C. You just put for determine the maximum temperature this formula Tmax equal to Tw plus Qg by 6k R square. This is the formula, right? Tmax equal to Tw plus Qg by 6k R square. So Tmax you get 15.4x. The heat flow from the outer surface of the orange is simple Qg into 4 by 3 pi R cube. This formula. Qg known, R known, all the parameters known, 21.961. That's all.